Hello again everyone, welcome back to ptet.chemistry channel. So in this lecture tutorial, we'll continue this mole and the Avogadro constant. This is to do with the idea of concentration, which is to do with solution chemistry. So in the previous lecture tutorials, we have covered the idea of mole calculations involving masses. So mole equal to mass in gram divided by molar mass or relative atomic mass in gram per mole. In the last lecture tutorial, we also talked about mole of gases is to do with volume of gas, where the volume of gas, if it is in dm cube, then we divide that by 24 dm cube per mole, which is to do with the molar volume of gas, where 1 mole of any gas occupies 24 dm cube at room temperature and pressure, and that is as given in your periodic table for an O-level or IGCSE level exam, as would for any 14 to 16 years old chemistry curriculum all around the world. So in this particular syllabus content, as outlined, candidates, meaning you, should be able to state that concentration is to do with gram per dm cube. So this is the mass of it dissolved in 1 dm cube of water. Or you can express it as mole of the substance dissolved in 1 dm cube. So per dm cube there means per 1 dm cube of water. This water is typically distilled or deionized water, meaning it's pure water. So per 1 dm cube of deionized or distilled water with no other dissolved ions except for that thing that you are dissolving it in, where there's the concentration of that substance, you dissolve a certain mass of it, which you can convert to the mole, because if you know the substance, you can work out the MR, and gram divided by the MR will give you the mole in the same volume of distilled or deionized water. So there's a relationship between these two that we'll talk about in this particular lecture tutorial. And we also have these experimental data to calculate the concentration of a solution in this thing called titration. Titration is one of the most common paper 3, or what we call a practical component type of questions. Any 14 to 16 years old chemistry curriculum will prepare you for at least one titration experiment, where we could do acid and base titration, or where we could do a redox titration. You might not have heard of redox, but redox is something you will have become accustomed to in a couple of months from now, once you do a topic called electrochemistry. Okay, anyway, just take my word for it now. So titration involves certain experimental setup, and that's something we'll discuss as well, and we'll be using this idea of we'll be thinking about it in a little bit. As I said, the term solution refers to when you dissolve in water, there's deionized or distilled water. This is a pure substance. Solid, liquid or gas is a pure substance. When you dissolve in water, you get a mixture. So aqueous is always a mixture because it's that substance dissolved in water. So when you see something solution, it means it's something dissolved in water. And ionic compounds such as sodium chloride or table salt dissolve in water. Solute is the substance that dissolves in the solvent. Solvent is the substance that you use to dissolve the solute. So you gotta be very clear what is solute and what is solvent. Solute is that substance that you dissolve in the solvent. Solvent is the substance that you use to dissolve the solute. NaCl dissolve in water. NaCl is the solute. Water is the solvent which you use to dissolve the salt. As mentioned, concentration can be expressed in mass of the solute, the substance, the mass of the substance, per 1 dm cube. This is gram per dm cube. This is just gram per dm cube, which is the same as gram over dm cube, which is the same as gram dm minus 3. This is just the rule of indices, which you have come across in mathematics, whether you have or whether you will eventually, certainly in your O-level IGCSE mathematics, you have come across the idea of these type of indices, where it's divided by that, so it becomes a minus instead. You can also have a relationship to mole per dm cube. This is called molar concentration. It's called molar concentration because it's to do with mole per dm cube. So whenever someone say molar concentrations, they mean mole per dm cube. Whenever someone say mass concentration means how much of the mass, which is gram, divided by the volume of the solvent, which is per 1 dnq of the solvent, typically is water. Now there's this formula, which again, previously we talked about this formula involving masses, where you're given mass is mass over mR, the units cancel out to give you mole. If you're given the volume of gas, not solution, be careful, solution have volume, gas has volume. Volume of solution is not the same as volume of gas. That's number one mistake that students make. Whenever you see gas, the volume does not represent solution. When you see volume of solution, it doesn't represent gas. So do not use molar volume of gas randomly, only for gases. Okay, this is only for gases. If you have solution, then we have to think about volume of solution. So that's why we have to think about, is it solution or is it a gas? You can think about it. The mole is concentration. Concentration is going to be mole per dm cube. Then you're going to be multiplying by the volume of solution. The volume of solution is in dm cube. So you can hopefully see that you can cancel out per dm cube and dm cube, and therefore giving you the quantity of mole of the solution. So this is your third and final formula. Mole of solution equal to concentration in mole per dm cube time volume of solution in dm cube. Okay, so this formula doesn't quite work when you have gram per dm cube. It only works with mole per dm cube because you want mole on the left hand side. The next idea is the idea called dilution. So when you have a concentrated solution, let's say you have Ribena, not too sure if everyone has had Ribena before. So if you have a syrup, let's say syrup, then what you do is you just add water. You just add H2O, then you are going to end up with a diluted syrup, which is less sweet. So this is less sweet, and then this is sweeter, much sweeter because it is much more concentrated. What we do is we just add water to it. The volume has increased. The volume has increased because I've just added water. Water is not the sugar. The sugar is what makes it sweet. So the amount of sugar I have in here is the exact same amount of sugar. So you think about it, the amount of sugar here in the syrup is going to be equal to the amount of sugar in the diluted solution, because all I've done is I have decreased the sweetness by adding water, but all I did was just adding water. I did not add sugar, so however much sugar I have in here, there's the amount of the substance is going to be equal to the amount of substance at the end. This is the very same idea that we are doing when we do dilution. So when you do dilution, whenever you do dilution, that means, are you just adding water? If you are just adding water, so just adding water, that means we are just making it less concentrated. So the mole before is equal to the mole after, because you haven't changed the mole. The mole remains the same because all you did was just adding water. You're just making it less concentrated. The term for the verb is called dilution. You are making it less concentrated. So the mole is going to be concentration in mole per dm cube times volume in dm cube. So the mole of the original solution equal to the mole of the diluted solution. Or the mole before you dilute is going to be equal to the mole after you dilute. Their concentration will be different, their volume will be different. Okay, as you can see, the final volume is bigger, so the final concentration will be smaller than the initial concentration. Once you know the mole relationship, the mole being the same, and you know this relationship from the previous equation, you should be all right. The next thing is basically how we are going to link mole per dm cube to gram per dm cube. So if I start off with mole equal to mass over mR. So this is mole, this is mass of mR. So what I do is, if I divide by dm cube both sides, then what I will get is I will get, let me use a different ink. I'll get mole over dm cube, I will get mass over dm cube, and I will get mR. So how does that work? That is mole per dm cube. So that is mole per dm cube. On the left hand side, mole over dm cube is mole per dm cube. Of course, I could write it as mol dm minus 3, whichever one you like, just stick with one, but not the two different form, which you can do mathematically speaking. Mass of it is in gram, because this is gram per mole. So what we're doing is gram per dm cube, and on the bottom there's just mr, which is gram per mole. So I hope you can see that gram per dm cube over gram per mole. In fact, perhaps you can't see it properly. So gram over dm cube divided by gram over mole is equal to gram over dm cube times mole over gram. And hopefully now you can see it. The gram and the gram cancel, and I'll get mole over dm cube, which is mole per dm cube. So do I need to know a different formula? Probably not. All you have to do is start from mole equal to mass over mr, and you can do a bit of math, and you can divide by dm cube. You get mole per dm cube is equal to mass per dm cube, mass in gram per volume in dm cube, divided by gram per mole, which is mr. So in this equation, you have just linked relative molecular mass with the molar concentration in mole per dm cube and the mass concentration in gram per dm cube. All right. So moving on to the next bit. So this is volumetric analysis. As mentioned in the second bit of the syllabus, in the statement made by the syllabus, the learning objective is to do with this idea of volumetric analysis. This is called titrametric analysis, or you can simply call it titration. So the technique or the method is called titration. They can also call it titrametric analysis, but the idea is to do with something to do with volume of solution, and we are analyzing stuff based on the volume of solution, the concentration of solution. That's why it's called a quantitative method. All right, so blah blah blah. This to do with fixed stoichiometric ratio. Stoichiometric meaning mole ratio. We have to think about balance equation. All right, so balance chemical equation. It was something that we started out before we deal with mass and moles and volumes a couple of lecture tutorials ago. As I mentioned, there are a couple of titrations. The common one include the acid-base reactions. This is basically what you call neutralization. But there is also other thing called redox reactions, where you will see these in the topic called electrochemistry, something to do with electricity and movement of electrons. That will be clearer when we come to it. But what is meant by titration? Titration is simply when you mix one solution from a burette. So you have a setup here. So this burette is supported on a retort stain. So you will be able to label this as a burette. This is a solution of unknown concentration. So you use a pipette. You use a pipette to take out fixed volume. So you have a fixed volume of that particular solution. You put it in there, you have a little bit of indicator, and then you run down whatever volume is required from the burette in order to turn or neutralize all of the acid or the base in here. If we are talking about acid-base reactions, if we're talking about this, then whatever color change, the indicator that the reaction is complete. So you have something called standard solution. Standard solution means you know the concentration, okay? Not to worry about this idea of equivalence point, but the idea is end point means is the end point is when the reaction has finished. There's a sharp color change. We need an indicator. An indicator is just a solution that will change color very sharply, and it will tell us reaction is done. It's just reached the point where just enough of these neutralize all the acid or the base. If only we have acid-base reaction, then we talk about neutralization. As I mentioned, if it is a redox reaction, then the color change will represent not an acid-base reaction, but it will represent the end of that particular redox reaction. Okay, so not to worry too much about it, but we talk about standard solution. Standard solution means you know its concentration. You know the concentration of a standard solution. So this thing are what we use to make up a standard solution. So how to make up a standard solution? I have a experimental tutorial video where you can watch how we work from the solid and how we can make up each and every one of these standard solution. We call them making up a standard solution. and the process is called standardization. We definitely need, depending on whether you start from solid, then you need an electronic balance to measure out the particular masses. If you start from a concentrated solution, you probably need a burette or a pipette to get a particular volume of the concentrated solution into each of these flasks. We definitely need volumetric flux. This idea is called volumetric flux. The technique was called volumetric analysis. Volumetric analysis was given here, and therefore these flasks are actually volumetric flasks. They are measured up to a particular volume. For example, in this one, this make it up to 1 dm cube. This is a 2 dm cube volumetric flask, etc, etc, etc. If you have 1 mole of the substance dissolved in 1 dm cube of solution, then you will have 1 mole over 1 dm cube. Then you will get 1 mole per dm cube. That is basically what it's saying there, which you could use this idea of molarity. Molarity refers to molar concentration. When someone pronounces this, they pronounce it as 1 molar. 1 molar means 1 mole per dm cube. It means the molar concentration in mole per dm cube is 1. On the other hand, if I have 1 mole of solute, so same amount of solute, but I have double the volume, so it's 1 mole over 2 dm cube, I will get 0.5 mole per dm cube. That's why the concentration is 0.5 molar, and so on and so forth. So that will give me 2 mole of solute in 1 dm cube, so 2 mole over 1 dm cube, that give me 2 mole per dm cube. I could of course use the other indices form, where it's 2 mole dm, 2 mole dm minus 3, that is mole, and then dm minus 3, that means mole per dm cube. And last but not least, we have this 1 mole over 500 cm cube. So we know that 1 dm cube is equal to 1000 cm cube from our last lecture tutorial, because 1 dm is 10 cm, so 1 dm cube, which is also 1 liter. 1 liter is also 1000 cm cube. So therefore 1 cm cube, now I want cm cube in dm cube, is going to be 1 over 1000 dm cube, because it is a smaller quantity. So 1 mole divided by 500 over 1000 dm cube, so there's 1 over 0.5, that give me 2 mole per dm cube. Alright, so I think we'll leave it there for this particular lecture tutorials, and we'll pick up with the rest of the work examples, where we'll manipulate the idea of concentrations and the idea on the mole, as well as the molar concentrations and the volume of solutions in the next lecture tutorial. So thank you for watching, and stay tuned for the next lecture tutorial, and don't forget to click the button on the bottom right to subscribe to the channel, and share the channel widely with all the people you think the channel will be useful for. And last but not least, follow me at ptet.chemistry on Instagram, Facebook, and Twitter if you use this social media platform. See you in the next lecture tutorial.